So first things first, so I have project 2 ready. It's about joint experiments. Now I had intended to release it last week and let you return it next Wednesday, but this might be too short. So I'm going to ask you, what due date would you like? So we have on Thursday, the week after, we have the midterm, which is then February 19th. So what do you say? Any other projects due in this time range? Operating systems? No? All right. What do you want? Two weeks? All right, but that's going to take you to the 19th. So it might be a little bit. So it's 15th, Monday, 16th, Tuesday, 16th, 16, okay. All right. So that gives us some time to give you feedback if Solmundur acts as quickly as last time. So just to, and then you can talk about this on the Monday and on Wednesday if there are some issues and so on. All right, okay. So sorry about being late. That's my fault, but I think this is reasonable. Okay. The other thing, I checked the assignments. I noticed that you returned 12, 12, 14, and 19, which is actually the smiley should be at 19. So I've basically, in some of my old classes, I've produced graphs that show grades and assignments, and it goes roughly like this. The people that return assignments get good grades. The people that don't, they get bad grades. Now, I cannot argue about the causal relationship because that can go either way. The people that don't get good grades, they don't show up, or the people that don't show up, they don't learn. I don't know. But anyway, these are 3 points, right? And if you don't take them, they're gone. And I've seen cases, I saw cases last fall where if students had submitted 1 or 2 more assignments, they would have bumped up half a grade. I've seen cases where if students had done more assignments, they would have passed the course. They passed the exam, but they failed on assignments. So, 3 points. And you learn. So I heard that yesterday was a little bit longer. So just getting up to speed with all the calculations takes some time. And I hope you just, submitted what you had after 90 minutes, because the point is not to make you necessarily finish, but I also hope that you will see that you need to practice. So you need to go to the book, do some exercises, because it's hard. This is really hard material. And to get it into your fingers, so there's straight path through your eyes, into your brain, down to your fingers, that takes exercise. So if this took a long time, then you should realize that you really need to practice. Practice makes perfect. And I mean, we would like to get you to the point where you can just look at it and you intuitively feel the curve. Like in the Matrix, you just you see it all in slow motion, and and you will get there with practice, but you need to practice. All right. So although the recordings are a little bit painful, I hope, then a little bit more painful than being here, I actually may have to use one next Tuesday. I'll let you know. So something that has come up and I might have to do, but I will try to work around it somehow. So I'll let you know on Piazza. I'll post something. Any questions so far? So we're going to leave query processing now. So if you have any questions about that, final things to think about, this is a perfect time. If not, then let's start. So basically, we are going to talk about something called concurrency control. So it's, we'll find out there are other ways to do this than locking. But locking is sort of conceptually simpler. So I'll start with that and then work my way through the other thing. But concurrency means people working on the same data at the same time. And so, you can kind of obviously think about what happens if you don't control it, right? You just updated something, I overwrite your stuff, then you commit, then I abort. What happens? What should be the correct data in there? Or even worse, you write something, I read it, I do something, you abort. So I saw data that never existed. Remember, atomic? So either everything happens or nothing. And so I saw data that actually, in theory, never existed. And so that's the kind of thing we have to control. This is why it's called concurrency control. So we've talked about transactions, right? It's basically a group of operations to the database. We talked about the all or nothing execution, the isolation, and all this stuff, right? So remember this, ACID. What's ACID? Say it, everybody. Yes? What? C? What's the C? Consistency? Everybody, come on. Isolation, come on. Durability, thank you. So I need a choir. So basically, you should be at the point where if somebody wakes you up in the middle of the night, says transactions, and you just go, atomic consistency, isolation, durability, and then you wake up. All right. So you really need to know this. Anyway, so if you read the book, they will say one execution of a user program. I think that's a horrible explanation, because a user program, right, it's basically an exe file that you run, and it's going to run for maybe days. And so you're not going to have a transaction running for days. So it's basically, each program will give you many transactions, but just think of it as sort of a logical operation. And, the bank transfer is the obvious thing. You take money from one account, put into the other. There might be some more complicated things like, you open up an account and you have to do some other bookkeeping and so on. So there might be some things that you want to happen together. Now, in the database tuning, you learn that sometimes it's a good idea to break transactions up into many smaller things, even though it's a little bit trickier to program because, of performance issues and so on. So have you used transactions, in projects and so on? A little bit? Some people? All right, it's okay. Well, 2 or 3 transactions, yes. All right. And logically it's easy. You say begin transaction or start transaction, depending on your system. You end with a commit or end. And if you say commit, then the role of the system is to make sure that the thing is durable and so on. You can also say abort, in which case the system should remove your operations and your impact on the database somehow. So that's, that's a failure. Then there are ways to do some intermediate things that you can basically put a save point and then roll back to the save point and then continue from there. So if you have a long transaction, you might put save points and then you just have to roll back part of it and then you can continue. Why would you abort a transaction? You might detect an error, for example. Yes. Somebody has some wrong input in some of the forms. Okay, so you try to reference something, it doesn't exist. That's another thing that might happen, yes? All right, so in banking, you might have insufficient funds. That's one way, yeah. So you try to withdraw, the money is not there, you're abort. All right, so there's, tons of different things. What could be other reasons? Do you know of any other reasons why transactions might be aborted other than what you doing it? Timeout, for example. You're trying to connect to a server somewhere, it just, doesn't do anything, or you might timeout. You can say, well, I cannot complete. Anything else you've heard about that could happen? They're competing with each other. Yeah. So you might have two transactions that are trying to compete for resources, and someone will get to this later on, that they are kind of waiting for each other and they get stuck. That's a deadlock. Yes. So we'll get to that. So there are different ways. And of course, if you are in the middle of a transaction and your server goes down, just crashes completely, loses everything in memory, then that transaction has to be aborted. You can't continue, obviously. So, there's different reasons why you might do this. Okay, so we got the properties, atomicity, consistency, isolation, durability. You know what this means, so let's not go through there. Well, we can talk a little bit about it. So consistency, it's actually interesting. So the database as such doesn't really think about consistency. I think we talked about this at some point. If I write my transfer in a way that I put almost all of the money into the other account, but I put some of it into my account, it's not a good transaction, right? But from a database point of view, it's fine. There's no logic. It's just, well, the consistent says that if you write your transactions in a way that move the database from one legal consistent state to another, then the database will help you to ensure that this is so. And so some of the things that it does do is, you have the key constraints. You can specify that some values are unique, and so you cannot, the database will enforce that. Foreign keys is another constraint that the database will enforce. You can write your own constraints, and then triggers is another means to enforce consistency. So there are things that the database does to help you, but generally it's the responsibility of the application programmer. For example, if you don't declare foreign keys, there's nothing that will help you. You can do whatever you want. So atomicity and durability we'll talk about when we start talking about recovery. And then the isolation, that's actually the one that's doing the concurrency control. It's sort of keeping you away from others. It's pretending that you are alone in the world. That's the concurrency control. Now, we'll talk about locking, why we lock, what to lock, how to lock really well. And so before we get to that, we need to talk about a thing called schedules. Talk about what the database sees when you're running a transaction. And then we'll talk about the kind of conflicts that could arise. I mentioned some before when, somebody's writing and I read it and then that other person aborts and I saw something that didn't exist. So that's a kind of conflict. Then we'll talk about a concept called serializability and another concept called recoverability. And that gives us sort of a class of schedules that we would like to work with, would like to enforce in the database system. And there's a class called strict schedules, which are kind of easy to enforce and they have good properties. And so we'll get to those. So what the database sees when you are running transactions is actually just a sequence of reads and writes, commits, aborts. That's all it sees. And so you have a particular transaction reading some record X or something from the index or maybe a whole file. It's depending on the way it's implemented. So it's just reading something, it's writing something, it might commit or it might abort. So from the point of view of a database system, looking up at the user, you just get back a sequence of this. Now later we'll add some locking and then these will be shared and exclusive. So when you look at schedules, look at this. If it's kind of obvious which transaction we're talking about, for example, if I draw like this, there's transaction 1 and transaction 2, and this is time, then I can just say read A, write A, etc. So just skip the subscript. Any questions? So you give your SQL, your inserts, your updates, deletes, whatever, and this is what the database system sees. Now, there's a property that basically guarantees isolation, and that's called serializability. And so a serial schedule, this is when you have a transaction, you complete it completely. And then I get one transaction and I complete it. And you have your transaction, you complete it. And so there's no interleaving. Nobody's running at the same time. This is called a serial schedule. for obvious reasons. So we just serialize everything, and one transaction completes fully, then the next transaction starts and completes, and so on. And then we can talk about equivalent schedules. So this is basically sort of math speak. If they do two schedules do the same thing to the database, then they are equivalent. And then we talk about the serializable schedule, which is equivalent to a serial schedule. So if we have a schedule, remember that's reads and writes and commits and aborts. If the final impact on the database is exactly the same as something that happened completely serially, then that's serializable. And you can guess that the serial schedule, like I said, that gives you isolation, obviously, because nothing is happening in concurrency. So if you have something that's serializable, that also gives you isolation. With me so far? And it's actually recently in sort of the online transaction processing where you have very short operations, people have started looking at systems that basically just do this. So if you have main memory systems with very short transactions, if you just run the transaction to completion, you don't need any locking. So there's very little overhead. And so if you see main memory, they might actually just do this, just give you serial things. But then if you come to that system and you run a query that takes 2 days, then everybody else has to stop. So, it's different trade-offs. All right, example. Here we have 2 transactions. And actually, if you took my course last fall, you will have seen this example. So the first transaction is a transfer. So it's actually adding money to one account and then removing from another. And the second one is calculating interest. So it's just adding 6% interest to the accounts. Now, if we start with A equals B equals 1,000, what do you get at the end of this? How fast is your math? So at this point, you got 1,100, right? And 900. And then you add 6%. So you get, don't be shy. You can do it. $11.66, yes. 954, right? I think. I'm wrong. 6 times 9. 54, yeah. All right. So this is an example of a serial schedule. First we do the transfer, then we do the interest. Right? So this is called serial. This is serial. Now, what do we get here? We first do the interest and then the transfer. What's the result from this? So here you have 10,060 or 1,060 in each, right? And then you do the transfer. So we actually get what, 1160, and B is 960. Which is the correct version? Depends. On what does it depend? Excuse me. The programmer's intent, but you intended isolation, right? You intended to pretend there's nothing else going on. So yeah, okay. So basically, you say if I issued the transfer and you issued the thing, and whoever was first should complete first. Okay, that's actually a good answer. Now, another answer might be, if you own account A, then you prefer the top one. If you own account B, you prefer the lower one, right? From the database point of view, there is no right answer. Both are completely equivalent because both are serial, and so both give you isolation. The database system doesn't care, and even it won't care if one of them started earlier and completed later. It just says these are both fine, and the database system really doesn't care. And so I would kind of agree with you that generally speaking, you would prefer things to happen, in kind of order, but that's basically the database system doesn't give you that. It just gives you something that says whatever is serial, it's correct. And yeah, so, but that means that you could have, you can have two, things are not deterministic in a way. Different things might happen. All right, so this one. What's the result of this execution? Do you agree? Same as the first one? All right. Indeed it is. And so that means that this execution is serializable. And you can see there's a difference because here we actually have concurrency. We have two transactions going on at the same time. The result is equivalent to a serial thing, so it's a serializable schedule, and that means we actually have isolation. This is fine. This one, what happens? Same as number 2. Agree? All right. You've gotten into the habit of nodding when I ask agree, so I'll try to ask you something, so where you can't agree. But that's another serializable schedule. Now, which of these is the correct one? Number 3 and number 4? It doesn't matter. And that's the point. So which of 1, 2, 3, 4 is better? Or best? Or, if I ask you, is 1 and 2 better than 3 or 4? Yeah, it depends on load. And so from the point of view of the database system, they're all equivalent. Now, you could argue that 3 or 4 are better in the way that things are happening concurrently. So you could actually say that if all you could do is 1 and 2, then your database system might have problems. Now, if you look at the response time, actually 1 and 2 have better average response time because in the top one, the first transaction finishes earlier than the second one. So in that way, you can argue that this is better, but probably there might be, if you have concurrent execution, you have more opportunities for sharing. If one transaction is waiting for a disk I/O to happen, the other one can proceed with CPU computation and so on. So generally speaking, concurrency is better. So, but from the database point of view, from the theory point of view, it's all equivalent. All right, so this one, what happens? What is the outcome of this one? Wrong. Compared to the others, you can say it's wrong, yes. So A, we do 1100 and then we add the interest, right? So we get A equals 1166. And then B, we add the interest, so we're now at 1060. And then we subtract, so we're at 960. Agree with this? So for the owner of A, or if the owner has both accounts, this is great, right? For the bank, not so much. But if you swap the operations A and B, then for the owner it's bad, and for the bank it's good. So in any case, somebody loses, and you don't want this. So that's basically an example of something that is not serializable. It's not equivalent to some serial schedule. And so the database, what does the database think about the last one? It's bad. You really don't want this. So if you could run this, then you don't have isolation. Then you don't enforce isolation because T1 is impacted by T2 and T2 is impacted by T1 in a way that could never happen in a serializable way. So the kind of schedule conflicts that we have, we can sort of group them into three things. One is called a dirty read. So this is when you have a transaction that writes something, somebody else reads it, and then the first one aborts. Remember, this is the example I gave earlier. So basically, you have a value here of A that because of atomicity didn't exist. See what I mean? Yes, it was written somewhere, but according to the three other transactions, it didn't exist. And then this guy read it, made some decisions, and wrote something else and then committed. So it gave back answer to the user saying, well, you got enough money to do this or whatever, and then it's gone. So this might lead to some crazy stuff happening, right? Not enough money, but yeah. And so also, if you think about how can you remove the effect of this right, how do you go back? Yeah, you have to lock. You have to prevent this. So we'll get to this. But if you actually allow this conflict to happen, what should be the value of A after? How can you go back? How can you recover the database to consistent state? You might go to the old value that was in A before T1, but then you've lost the impact of T2. Or you might stick with your old value, the new value of T2, but then, something strange happened. You added 100 to A, B added 100 to A, and then at the end you have 200 where you only should have 100. Stuff like this. So yeah, so the question is, do we have to abort both of them? Basically, if you wanted to allow transactions, we'll get to this, it's called recoverable schedules. If you want to allow transactions to read from other transactions, uncommitted things, then you have to abort, if you abort the first one, you have to abort the second one, yes. And you indeed have to abort them in the order that they happened, so that they refresh. So if you're allowed, and this is sometimes done in what's called optimistic, you just assume that things would happen and then hope for the best, then this commit here couldn't happen and you would have to wait until here, and then indeed you would have an abort. Do you have some cascading effect? So this would be an example of a cascading effect. It's basically cascading the abort to the transactions that read your value. However, when we get to locking, we'll see that we just prevent this. We just avoid this conflict by locking. And so this won't happen. We'll have some other things that might cascade with deadlocks, for example. But we'll just avoid this. But just to know, this is called a dirty read, because when you talk about, we'll talk about something called isolation levels, which you can set lower isolation levels. You can avoid serializable because it has negative performance impact. And so one of the things that you will see is you might see is, well, actually maybe they don't allow you dirty read, but you'll see the unreadable read and the overwriting uncommitted data. You'll see this. All right, so that was a dirty read. Then you have something called unrepeatable read. And sort of the prototypical way to explain this is that you have a transaction that is reading a value, then some other transaction changes it, and then the first one for some reason has to read it again and finds a different value. Or alternatively, you can say it actually makes some decision based on the previous read that's now outdated. What if, for example, if you're adding money to your account, you add 100, or you read 1,000, You read 1,000, you add 100, you get 1,100, you add 100, you get 1,100. Right? So you lost one of the writes. So this is called a read-write conflict because you start with a read and then you mess up with the write. All right? So that's, this is the second example here. And then you get overwriting uncommitted data, which is again similar. So but in this case, there's no reads. Somebody writes a value, somebody else writes a value, changes another value, commits, and then the first one changes the same value. So you can, the typical example of this is to say you have triggers that try to make sure that two people have the same salary. So I should have the same salary as you. And so I get a salary raise, and so that's written in A, you get a salary raise maybe, and so you write your salary, you write my salary, and then I try to update your salary. And now they are actually both incorrect. I got your salary and you got mine. See what I mean? So this is a standard example. So this is overwriting uncommitted data. So there's no reads involved, but just writing, and if you do this in the wrong order, then you're in trouble. So these are the these are the three conflicts. So how do we do this? Well, basically work with something called conflict serializability, and that's another kind of theory thing. We say two schedules are conflict equivalent if they have the same operations of the same transactions, and whenever you have two things that could conflict, they're in the same order. So you don't sort of reorder things that might mess each other up. And then we say that the schedule is conflict serializable if it's equivalent to a serial schedule. And there's actually a way to find these schedules, which is called the precedence graph. So in this, you basically have a node for every committed transaction, and you put an arrow from transaction I to J if I is first and then conflicts with action of TJ. So let's take an example. So you got transaction 1 reading A and transaction 2 writing A. That's a conflict, right? Because A hasn't committed, then we're invalidating its read. So that means we put an arrow from T1 to T2. And then actually transaction 2 commits, transaction 1 writes A. Now we have a conflict here that we wrote over the value of C. Actually, that's probably not true. We should not have the commit here. And then we have transaction C, or 3, basically writing over the value from T1, and so we have an arrow here. And basically, if we have a cycle, then it's not serializable. If your conflict operation is after me, and I have a conflict operation after you, then we cannot straighten out the conflict. There's no way to find an easy order that has no conflict. And basically, the locking algorithm we'll talk about, it avoids these cycles. And so if you have a cycle, what you'll end up with is you might end up with a deadlock. But you'll avoid this. So a couple of examples. Remember the example that we had where you had the transfer and you had the interest calculation sort of mixed in between. And in this case, you have a cycle in your graph because you have a conflict here and you have a conflict here. Clear? But the latter one, reading A, writing A, then this transaction reads A and writes A, does something with C, then transaction 1 is reading and writing B, and then transaction 3 is reading and writing B. This one is actually conflict serializable. So it's equivalent to T1 happening first, and then T2, T3, or T3, T2. You know a topological sort? You heard about this from graph theory or algorithms maybe? It's basically traversing a graph in following arrows, and so where you don't really care if you have a set of nodes, you don't care which arrow you follow, as long as you don't go in cycles. And so any topological sort would do. But anyway, so but again, this is just to know what could happen if you don't do locking or if you don't worry about this. And indeed, one of the examples here, this actually can happen with what's called snapshot isolation, which is very popular with Oracle and other systems. You can have situations like this, which people just basically ignore. But so what? Sorry, can you repeat? So what's the default locking level? So we get to this in SQL Server. It's basically the I think it actually allows unrepeatable reads. So it's yeah. But we'll get to this. I have this in my slides somewhere. We'll get to the isolation levels. So it's basically typically systems start off with some lower level for performance, because otherwise you have to do a lot of locking. And you need to know about this. All right. So, all right. So basically, we have this thing called conflict serializable schedules. The two-phase locking gives us that. There are ways that you might have serializable schedules that is, how do you say, more flexible, but it's just hard to enforce. Strict two-phase locking gives you nice things. And then we have classes of schedules that are called recoverable. So we talked about this, remember, when we allow a transaction to read and do something with values that are uncommitted, we cannot recover. We don't know what's the old value to put into the database. And so anything that if you only commit when all your suppliers have committed, then we can recover. So that's a recoverable schedule. Then we have no cascading abort, which is nice in the way that even if I abort, then nobody else has to abort. And in that case, we can only read values from committed transactions, because otherwise we'd have to cascade the abort. And then we have something called strict schedules, where we're only reading and overwriting values of committed transactions. So we only read and we only overwrite them. And so for this, if we do the strict schedules, then recovery tends to be fairly easy. We don't have to, go back long in time. So we have these things, schedules, and so basically strict two-phase locking is somewhere here. So we got these, conflict serializable, we got these strict things, and with strict two-phase locking, we're here. So it's a fairly narrow subset of schedules. And again, there might be schedules in this that are serializable, are recoverable, but we don't allow with strict two-phase locking. All right, so let's take a 5-minute break now, and then we'll get to the two-phase locking. We'll start avoiding all this stuff. All right. So we got to this point where we were going to talk about strict two-phase locking, and the reason why we do it, it's very easy. It gives you the serializability that we like, and when you need to recover, it's minimal work. So that's what to lock when, and I'll talk about the strict two-phase locking. I'll talk about pros and cons, and then we'll talk about a couple of problems, deadlock and phantom problem, and then we get to the levels of isolation that you're asking about and talk a little bit more about that. And so your assignment for next week will basically be to play with a level of isolation, see if you can produce the phantom problem, which should be possible in SQL Server and so on. All right, so strict two-phase locking, it's extremely simple. I think even my grandmother could learn this, and she's dead. So there are 3 rules, and so there are different ways to put this forward, but I like this version, which is to say there are 3 rules. You need to get a lock before you get any data. So before you access a record, or depending on what's locked, you need to get a lock. If you want to read, you have a shared lock. If you want to write, you get an exclusive lock. And the names are kind of obvious, right? Shared means they're sharing. Exclusive means you're the only one. And that's actually rule number 2. If some transaction has an exclusive lock, no other transaction can't get any lock. And then 3, all locks are released at commit time. So when you commit, you just drop the locks. So this is strict two-phase locking. Clear enough? So we have this will not work very well on the recording, but can you come here? So we're going to demonstrate locking. So this is your record. Left hand, it's a shared lock. Like this. Put it on, right hand, exclusive lock, like this. All right? Shared is your left, the other left. All right. So I'm going to read something. I got a shared lock. You're going to read something. Got a shared lock. Okay, so we're both here. Now I want to write it. I can't. See what happens? Because he's already reading it. So I got to wait. You stop reading. I can get it. I'm writing. You want to read it? Haha, can't. I got the lock, right? See what's happening? So the shared, it's still there, out there. Anybody can touch it. Exclusive, you got it. Fair enough. So let's do an example. So we remember this one we didn't like because we didn't get serializable execution. Now if we have a strict two-phase. Okay, so let's go back here. So here I wasn't doing reads and writes. I got an exclusive lock. I read and I write. I get an exclusive lock. I read and I write. I get an exclusive lock to B, read and write, and so on. So I put in locks. With strict two-phase locking, I get an exclusive lock on A. I read and I write. And then transaction 2 tries to get an exclusive lock and can't because transaction 1 has it. So it's going to wait. What happens while transaction 2 is waiting? What could happen? Anybody? Something else can go on, right? The system marches on, and who's waiting in line to do something? Transaction 2, right? No, 1, sorry, transaction 1. Because that is issuing, now it's already progressing, it's, can march on. So that's actually what could happen next. Transaction 1 wants to continue, read, gets an exclusive lock on B, reads it, then writes it, and then commits. Should it release the lock on A before doing the B? No, because remember rule 3? You keep all the locks until commit. Yeah, because otherwise you may have serious trouble. You may violate the rules. and you may have things. So on commit, you release, and that actually means that transaction 2 can continue, and so it's going to complete. So what happened? We actually enforced serial execution, not just serializable, in this case serial, but because it's so simple. If with more complex execution, we might enforce serializable executions, but not serial. But we basically avoided this conflict. See what happened? By making somebody wait. We detected a conflict happening, which is the, which is the fact that only one person can have an exclusive lock. That's the part that avoids the conflicts. Clear? So you're even as smart as my grandmother. I'm happy. She was smart, by the way, but Anyway, so there's some theory about strict two-phase locking being conflict serializable and strict and so on, but I'm not gonna get too much into this. I would like you to be able to use this and understand what's going on. So there's something called the compatibility matrix, and it's very simple in this case, but we'll get to more detailed lock modes later on. So the way you read this is that you have, this is already going on. You have something with a lock on a particular record. And then this is what happens next. Some other transaction comes in and requests a lock. And this matrix, this simple matrix, just says that if your first transaction has a shared lock and the new transaction requests a shared lock, then it can grant it. If your old transaction had an exclusive lock, you want a shared lock, you cannot. If your old transaction had a shared lock and you want an exclusive lock, you cannot. So it's just one concurrent thing that can happen. This is reading. And like I said, we will get to more complex lock modes where there are more check marks. But this one is very simple. Now the book does talk, I think, a little bit about what's called basic and conservative two-phase locking. And basically means what you asked. It says that you could actually release, or something similar, says that once you can release locks at some point, not necessarily at commit time, but the rule is that once you have started releasing locks, you cannot get new ones. So you couldn't go up, down, and then up in the number of locks. You can acquire locks and then release. This could sometimes be faster because you might give access to some of your records here in the end, and then things can progress faster. So that's the blue one. That's the basic. You just acquire locks when needed, and you can unlock once you've gotten all your locks. You can start unlocking. But you cannot unlock before you use something. You just can release some of your locks. Then they have something called conservative, which basically says in the beginning, I get all my locks. All the locks I'll ever need, I get in the beginning. Then at some point, I can start releasing. And then you have the strict, which is different. It acquires the lock when it needs them, and then waits until commit to release them. So why don't we do the blue one? Excuse me. In the blue one, you might abort